Hi, everybody. Okay, so the last thing we're going to talk about in chapter 4 is kind of taking all this stuff and putting it together, but applying it in order to figure out what chemical formulas are for covalent compounds in the first place, right? So we talked about a strategy for ionic compounds where we determine the charge on the cation, determine the charge on the anion, and we put them together in a ratio such that their charges add up to 0. We don't have that type of a strategy for covalent compounds, though, because there are no charges that are involved in covalent compounds. So how do we know that carbon dioxide is CO2 other than the fact that we've been told it's carbon dioxide, right? So how do we figure out these in chemical formulas from data, right? Because that's all we have is data. We can't count atoms and molecules. How can we take data and determine what the chemical formulas are? So that's what we're going to talk about in terms of these empirical and molecular formulas. Okay, so first things first, let's define what the difference between an empirical and a molecular formula are. Okay, so an empirical formula, that's kind of what we've been talking about without defining it as such with ionic compounds. Okay, so ionic compounds, we talked about how those, like sodium chloride, is this huge repeating pattern of sodium chloride, sodium chloride, sodium chloride, sodium chloride forever and ever. And we said that the smallest repeating unit in that crystal was NaCl, right? That's the empirical formula of sodium chloride. It's the smallest whole number ratio of all of the elements in the compound. How can we reduce, if we had 10 sodiums and 10 chlorides, that ratio gets reduced down to 1 sodium and 1 chloride. That's the smallest whole number ratio. The molecular formula, however, the molecular formula is, again, more pertinent for covalent compounds. So this concept is mostly for covalent compounds. It's the actual number of the atoms in a given molecule. Okay, so we're not talking about the smallest whole number ratio. We're talking about if we were able to grab a molecule of what we're talking about and count each of the quantity of each of the atoms in that molecule. That would be the molecular formula. Okay, so let me give you an example of how these two things can be different. Okay, so let's consider water and hydrogen peroxide. Both are covalent compounds because they're both hydrogen and oxygen, right? The molecular formula of water is H2O. If we looked at a molecule of water, there would be 2 hydrogens and 1 oxygen. That's what it actually exists as. The molecular formula of hydrogen peroxide, if we looked at a molecule, there'd be 2 hydrogens and 2 oxygens in that molecule. Okay? Now, molecular formula is what we're always trying to figure out. That's the end game here. But the way that we get to the molecular formula is through the empirical formula. Okay, so remember, empirical formula is the smallest whole number ratio. So when people were first trying to figure out the chemical formula of hydrogen peroxide, they noticed that there were the same number of moles of hydrogen and oxygen in every sample, right? A 1-to-1 ratio is the simplest whole number ratio that hydrogen and oxygen exist in. We needed to do another experiment to figure out what the actual molecular formula is. So again, empirical formula is the first step to figuring out what the molecular formula actually is. Sometimes our molecular and empirical formulas are the same, but sometimes they're different, and we need to do another calculation to figure out what the actual molecular formula is. So we're going to do a couple practice problems here to kind of show you what I mean by this concept, because out of context it's kind of like, what are you talking about? But if we do a couple practice problems, we might be able to see kind of the distinction between these two things. Okay, so first things first, let's remind ourselves about what these subscripts actually mean. Okay, so remember, the subscripts in a chemical formula are molar ratios. Okay, so what is a ratio? A ratio is when we take one number, divide it by the other, and figure out what the answer to that division is. It's a comparison between two things. Okay, so if we want to get a whole number ratio, because remember John Dalton said that elements combine together in compounds to make whole number ratios. if we want to get a whole number ratio, we're going to take a big number and divide by a smaller number in order to get a ratio greater than 1. Okay, so if we look at this problem here, we have an unknown compound that has 0.0121 moles of phosphorus and 0.0364 moles of chlorine. What is the chemical formula of this compound? So what we're trying to figure out here, we have phosphorus, we have chlorine, and we don't know what these subscripts are. We don't know if it's PCl, we don't know if it's PCl2, we don't know if it's PCl8. We have no idea, right? Because a covalent compound does not rely on charges. There are no charges. There's no ions in a covalent compound. So the way that we need to figure this out is we need to take the number of moles of each of our components and take a ratio of those two to figure out what the simplest whole number ratio is between those. Okay, so if we want a whole number ratio, again, we take the bigger number and divide by the smaller number and see what we get. Okay, so bigger number is 0.0364. That's moles of chlorine. Okay, so we're going to keep our units attached. And we're going to, oops, sorry, that's a really crooked line. We're going to divide by our smaller number, 0.0121 moles of phosphorus. Okay, so if we do that division, if we take a ratio between those numbers, the answer that we get is, our calculator tells us about 3.01. What does that mean? Okay, but remember, units only cancel with each other if they're exactly identical, right? So moles of chlorine and moles of phosphorus, those don't cancel with each other. So we can carry those units over to the other side. So this means that there is 3.01 moles of chlorine. Now when we divide two numbers, right, our calculator just tells us a single number, but what is a whole number always a ratio out of? 3.01 is the same as writing 3.01 over 1, right? So this ratio tells us that there is 3.01 moles of chlorine per every 1 mole of phosphorus, which is very close to saying there are 3 moles of chlorine per every 1 mole of phosphorus. So now we have our simple whole number ratio. The 3 is the subscript that goes with the chlorine. The 1 is the subscript that goes with the phosphorus. So our chemical formula is 1 phosphorus, 3 chlorines. Okay, so what would the name of this compound be? This would be phosphorus trichloride, because it's a covalent compound. Okay? So that's what we're going to do with these next couple of practice problems. In order to find a chemical formula, we need to find how many moles of each component we have. Once we find how many moles of each component we have, we take a ratio, and that ratio tells us our subscripts in our chemical formula. Okay? All right, so let's go one step further. Right, let's do so this is just what we said. So whenever we want to determine an empirical formula, what we're doing is we have to determine the moles of each component and then take a ratio. So here's another problem, but we're taking it one step further. Now we're trying to find a chemical formula from mass percentages. Right, so remembering what a mass percentage was from the very first video of this chapter playlist. Okay, determine its empirical formula. Okay, now what we have to do with this information, right? We first have to determine how many moles of iron and sulfur we have in our compound. But do we have a strategy for taking a mass percent and converting that into moles? How do we know how to get into moles from easily, right? In one step. What's a unit that we can convert to moles really easily? Well, we can either use atoms using Avogadro's number, or we can use a mass using the molar mass. right? Can we take these mass percentages and get a mass to convert to moles? Well, yes, we can, because remember what we talked about in the very first video with the law of constant composition? The law of constant composition says that no matter how much I have, whether I have a tiny speck of our compound or a huge boulder of our compound, these mass percentages are exactly the same no matter how much I start with. So isn't it okay, because they're the same no matter what, can't I just assume a random quantity of my compound and figure out the mass of iron and the mass of sulfur using the mass percentages, right? So what if I just took a really simple round number and I said I had 100 grams of my compound, right? Because no matter how much I have, those ratios are always set, right? So if I had 100 grams of my pyrite, this is another mineral, okay? If I had 100 grams of my pyrite, what would the mass of iron be if it's 46.63% iron? Well, 46.63% of 100 grams is 46.63 grams of iron, right? So I can use that law of constant composition just to assume a starting mass. And you can assume anything. You can assume 100 grams. You can assume 1 gram. You can assume 585 grams. It doesn't matter. You're going to come up with the same answer because those mass percentages are constant. They're always the same. Okay, but 100 is just nice and round and easy. I don't have to think about it too much. Okay, so of my 100 grams, 46.63 grams is iron and 53.37 grams is sulfur. Boom. Now I have masses of my elements. How can I find the moles of my elements? Right? So if you can do that on your own, pause the video, see if you can find how many moles of each of iron you have and how many moles of sulfur you have. Okay, so how we go from grams to moles, remember we find on the periodic table, we find the molar masses of those two components from the periodic table. So we know that 1 mole of iron, we look on the periodic table, has a mass of 55.85 grams. Remember, I organize it this way so my units cancel. I know that 1 mole of sulfur has a mass of 32.06 grams. Remember, I have to take the molar mass from the species that I'm talking about, okay? I organize it so that my units cancel, and then I just multiply and divide. So the number of moles of iron that I have, again, we have to keep our sig figs. This is really important for these types of problems, is to keep sig figs. Okay, so if I have 4, I need to have 4. 0.8349 moles of iron and 1.665 moles of sulfur. Okay? Am I done? What do I have to do next? Well, I determined the moles of each component. Now I have to take a ratio of those two, right? The number of moles doesn't tell me my subscript. It's the ratio of the moles that tells me my subscripts. Okay, so again, we're right where we started with this problem right here. We had moles, we took a ratio, and that ratio gave us our subscripts. So again, we're taking the bigger number, dividing by the smaller number. So now I take 1.665 moles of sulfur. I divide by the smaller number, 0.8349 moles of iron. I divide those two numbers. My calculator tells me 1.994. Right? Now that is within, I would say, if this number is within 0.01 of a whole number, which it is, you can round it up to round it up or round it down to the nearest whole number. So this is about 2. That's safe to say that it's about 2. We're going to do one in the last problem where we can't make that rounding distinction. Okay, so again, any whole number is a ratio over 1. So there are 2 moles of sulfur per every 1 mole of iron, and those are my subscripts. So my 1 goes with my iron, Fe, my 2 goes with my sulfur, S2. Done. Okay? All right, so let's do one more. Oh, and then, sorry, this is a figure from your textbook that kind of shows the pathway that we went here. So we started with mass percentages. We assumed a mass of our compound to get a mass of our iron and a mass of our sulfur. We used the molar mass to find how many moles of our 2 elements we had. And then we take a ratio to find that empirical formula. Okay, so that last step is super important. It's the ratio between those two mole quantities that gives us our subscripts. All right, last problem. Okay, so this might be a good time for you to pause and try and work on it on your own. So same type of problem, but now we just have 3 components. Okay, we have carbon, hydrogen, and oxygen. Okay, so first steps first, just like what we did before, we need to find the moles of carbon, of hydrogen, and of oxygen, and then take a ratio of the 3. So pause it, work on it on your own, come back and we'll do it together. I'm going to go through this part relatively quickly because it's the same idea as before. Right, so again, we're going to assume 100 grams of our compound. In our 100 grams, 40.92% is carbon, so 40.92 grams is carbon. We've got 4.579 grams of hydrogen and 54.51 grams of oxygen. Okay, so I'm going to take each of those, use the molar mass of each to convert into moles. Okay, remember to take the correct molar mass from the periodic table. And remember, we're always just organizing our units so that our units cancel out and give us the units that we want. Okay, so multiplying all these out, we get 3.407 moles of carbon. We get 4.543 moles of hydrogen, and we get 3.407 moles of oxygen. Okay? Now, what we're trying to do here, remember, we have a compound of carbon, hydrogen, and oxygen, and we're trying to figure out what those subscripts are, X, Y, and Z. Okay? Now, looking at our mole data here, what can you say about 2 of our subscripts? Right? So do you see how carbon and oxygen are exactly the same? That means that whatever subscript we write for carbon, we're going to write that exact same subscript for oxygen because the ratio between those 2 moles is 1 to 1. Right? 3.407 is the same as 3.407. Right? So when we're thinking about the ratio that we have to take, right, all we have to do is just take a ratio between hydrogen and carbon or oxygen because they're the same. Okay, so we're still going to take the bigger number, divide by the smaller number, but the smaller number is the same for each of them. Okay, so I'm going to take 4.543 moles of hydrogen, and I divide by 3.407 moles. This is carbon or oxygen. It's the same number. Okay, so I divide that out. What do you get? So we get 1.333 over 1. Now this is not within our 0.01 threshold of a whole number. Right? This is 1.333. That's a bit too, that's too much, we're taking too much liberty with our rounding there to say that it's a 1-to-1 ratio. That's too far away from 1-to-1 to round. That's actually something different than 1-to-1. Okay, so how can we get this into a whole number ratio? Because our chemical formula is not CH1.3330. right? John Dalton said that elements combine together in whole number ratios to form compounds. We can't have a fraction of an atom. So how do we get this into a whole number, right? Well, what we can do is we can multiply the top and the bottom by the same number in order to make them both whole numbers. Okay, so what am I going to multiply top and bottom by to get it into a whole number? Well, let's try, right? So let's multiply top and bottom by 2 over 2. Does 1.333 times 2 give me a whole number? Nope, it gives me 2.666. That's not within our 0.01 kind of threshold. What if I multiply it by 3 over 3? Well, that gives me pretty close to a whole number, right? That gives me 3.999 over 3. That we can safely say is about 4 over 3. Right? So see, if we get a ratio that's not a whole number, one of two things happened, right? So if it's not a whole number, then maybe you did your math wrong on your moles and you should go back and check. Maybe you took a wrong molar mass or something. If it's something like 1.333, then we can multiply by the same number top and bottom to get a whole number. What if it was 1.25 over 1? What would you multiply 1.25 over 1 in order to get a whole number ratio? Well, I would multiply that by 4 over 4 to get 5 over 4, right? So you see how you can kind of just manipulate the numbers, right? If you multiply the top and the bottom by the same thing, 5 divided by 4 is still 1.25. 4 divided by 3 is 1.333. It's the same ratio, it's just scaled up to a whole number. Okay, so if we take all of that, again, let's pull our moles over here so we know that there are 4 moles of hydrogen per every 3 moles of carbon or oxygen. Okay, so those become our subscripts in our chemical formula. So our empirical formula is C3H4O3. Okay? So the last part of this problem is we're talking about empirical formulas a lot, but what about those molecular formulas? Okay, so remember we said the empirical formula is kind of the intermediate step to getting to the molecular formula. Sometimes those two are the same, but sometimes they're different. Okay, so this is the information that we need, our molar mass of our actual compound of our molecular formula, to figure out what that molecular formula is. Okay, so we have another piece of information that we have. The molar mass of our compound was found to be 176.12 grams per mole. What is its molecular formula? Okay, so we have our molar mass of our actual compound. Why don't we find the molar mass of the empirical formula that we found? If those two numbers are the same, then we know that the empirical formula and the molecular formula are the same. If they're different, then we know that those two things would be different. Okay, so let's just start with saying, are they the same or are they different? Okay, so pause the video, find the molar mass of this compound here. Okay, so when we add up 3 carbons plus 4 hydrogens plus 3 oxygens, the molar mass that we get for this compound, molar mass of this, is 88.062 grams per mole. So we see that they are different. So we know that the molecular formula and the empirical formula are different from each other. But how do we know how do we know what the molecular formula is? Well, the way that we can do it, right, we figured out that these ratios are 3 to 4 to 3 ratio. Those have to stay the same. We can't change that. Just like we can't change the chemical formula of water, we can't change H2O 2 to 1 to H2O2 2 to 2. Because if we change our chemical formula from water, we get now hydrogen peroxide, which is a completely different substance. So remember, those subscripts, those are set. Our ratios are set. We can't change them. The only thing that we can do is scale them up, just like we did in the last part, right? So a compound with 3 carbons, a ratio of 3 to 4 to 3, a ratio of 6 to 8 to 6, that's still the same ratio, right? So what we can do is we can take a look at this molar mass and this molar mass, take a ratio of those two numbers, and see how those ratios compare. Okay, so if we take 100, again, we're doing big over small, 176.12 grams per mole. We divide by the molar mass that we found for our empirical formula, 88.062 grams per mole. What do we get when we divide those two numbers? 2. So what does that tell us? That tells us that our molecular formula is 2 times our empirical formula. Okay? So what we do is we take that empirical formula and we multiply all of those subscripts by the ratio that we just found. So we take our 3, we multiply it by 2 to get 6. We take our 4, multiply it by 2 to get 8, and take our 3, multiply by 2 to get 6. This is our molecular formula. And you can check your work. You can solve for the molar mass of this compound right here. The molar mass will come out to be 176.12. Okay, so all of this is just ratios. Ratios of elements to each other, ratio of molar masses to each other, as long as and it's always mole ratios. So the gist of almost all of the calculations that we're going to do, when in doubt, calculate the number of moles. Okay, and the way that we get there from a mass is from the molar mass. Okay?